Okay, guys, how's it going? So today we're gonna start off with the practice problem with relating Kc and manipulating it by changing the chemical equation, and then we're also going to talk about how we can connect Kp and Kc to each other. Okay, so let's get started. So at 700 degrees Celsius, our Kc value is given to us with a value of 20.4, and with that, that means that that essentially is giving us, if you remember, Kc is equal to the products over the reactants. That would be SO3 over SO2 and O2 to the 1/2 power, right? Okay, so it might help having like just a relationship and knowing that that is what Kc stands for. And then suddenly what we're doing, if you notice, it says what's the Kc for this reaction shown below, and this reaction has been manipulated such that we have multiplied all the coefficients by 2. So this became 2. If you multiply 2 times 1/2, you get 1, which is how you got that one. You get a 2 in front of this. So that is how we've done to this equation. So then let's just look what the Kc prime would be for that. If we did that, it'd be SO3 squared over O2 and SO2 squared. And if you notice, this Kc prime is essentially just our original Kc with every exponent raised to the second power. So essentially what we're doing is to relate these two, it's going to be that Kc prime is just equal to Kc to the second power. Another way of writing that, it would be that it's simply the same thing, SO3, the original Kc, SO2, and O2, raising every exponent to the second power. And that's how we relate our Kc to our Kc prime. So what do we learn from this? Well, we said, well, if you if you multiply some number through a chemical equation, so in this case we multiplied the number 2 by, through every coefficient, then you raise your original Kc to that power. So if I had multiplied the entire reaction by a factor of 1/3, well, then I would raise my Kc to a factor of 1/3. Okay. So then all we got to do is do a little bit of math. So then our new Kc prime, is equal to our original Kc, like I said, squared. So then that would give us a value of 20.4 to the second power. Okay. Let me calculate that really quick. Maybe that looks kind of ugly, so I'll go like that. There we go. So 20.4 to the second power. If we accommodate for 3 significant figures, it'll be 416. Okay. Remember that Kc is unitless, so we shouldn't have any units attached to this at all. Okay, so we have our new Kc. Remember, so just to recap, whatever factor you are multiplying your original equation by, you raise your original equilibrium constant to that factor. So in this case, the factor we multiplied was 2, so we raised our original Kc to that factor of 2. That's what I'm doing right here. It's worth saying that it's not always 2. Sometimes it's a half, sometimes it's a third. So just be comfortable with any number multiplying through an equation. Don't get comfortable with just 2. Okay, so moving on, we need to then get the Kp for this reaction, and we need to remember that we talked about this in class, that our Kp is easily solved through a simple equation where it's the Kc value multiplied by RT to this thing called delta N. And we just need to remember a few constants and what these variables represent, and then it would be a pretty simple process to solve for Kp. So all we got to do is remember that the R in this case, where Kp, the P is normally related to pressure. So if you look at our original equation, these are all gases. So instead of relating to concentrations like their molarity, we can instead use their partial pressures, and we can solve for a analogous Kp, an analogous equilibrium constant for pressures. Okay, so we're solving for this thing called Kp, but in order to solve for it, you need the original equilibrium constant, which is what we have. Because we're dealing with gases, the R we're going to use is 0.0821, liter ATM over mole K. You can remember that as your gas constant from Chem 101. And then the T, because of what's imposed by the gas law, liters over mole Kelvin. Sorry, I put liters on the bottom. So that means because of this liter term, this Kelvin term, we're going to have our temperature be in Kelvin. Okay? Because then the units would cancel. And then finally, we're dealing with this delta N term. And I'm sure I've talked to a bunch of you guys about this, but delta N, remember, anytime you have a delta, it's final minus initial. So that would be moles of gas. So final moles minus initial moles. Okay, so how many moles of gas did we have in the finals? Well, that would be, so let's just solve for our delta N in this case. Our delta N, well, we had 2 moles of gas to start with. And then initially we had 2 plus 1, that would be 3 moles. So that's the 2 and the 1 here I'm talking about. So that would be 2 minus 1. And that would give us, 2 minus 3. I apologize. I'm a little ahead of myself. So we have 2 minus 3. And that gives us a value of minus 1. So our delta N value is -1. And we can now plug in all the values that we've solved for and go ahead with this. I guess the only thing we didn't solve for was temperature. And just to remember, the temperature in Kelvin, well, we're given 700 degrees Celsius. So then we just have to multiply, or rather add that to 273, giving us 973 Kelvin. And then we can now use that. So just remember that if you're converting between Celsius and Kelvin, they're separated by the adding 273 to it. Okay, so now we can go forward. Let's finish it off. So then our Kp is going to be equal to our Kc that we solved for in the previous problem, so 416, multiplied by Rt, which is that 0.0821. I'm going to move all this other stuff just because it's getting kind of in the way. So let's see if I can get it out of the way. Just going to get it out of here. Okay. 0.0821. Make sure that you kind of are very careful with this in your calculator. I'll actually write it the way you should write it in your calculator. So that's 416. And then I do like a big bracket here. And then I would multiply R 0.0821 multiplied by temperature, which was 973 Kelvin. All raised to the -1 power, because that's our value of delta N. So then our Kp, we just got to solve for that. So that would be 416.0821 times 973 to the -1 power. And if we do that, we get a value of 5.20. Cool. So then our Kp was equal to 5.20, and our Kc value we solved for was 416. And you could just think of these two values as they're analogous, right? So Kc, remember, is a ratio of the products over the reactants, right? And Kp is the same thing as that. However, it's accommodating for the fact that these are gases. Okay. So it turns out that the equilibria is a little bit different with respect to gases. We don't really need to go any further than that, but that's essentially the concept that we're trying to get here. So what did we learn as a recap? Remember, if you multiply by some factor, we multiplied by 2 here, that is what you raise your original Kc value to. So we raised it to the 2nd power. And then to solve for Kp, you need the value of Kc through this equation. Kp equals Kc to the Rt delta N. And then we can just plug and chug and solve. Okay. Pretty easy problem. However, hopefully that clarifies any questions you guys might have. And then I will see you in the next video.